Right. So this is the goal of this one is to be able to change um, complex rectangular coordinates in the form a plus bi to complex polar form in the form r cosine theta plus I sine theta. So, quick review here of the complex plane. We have the reals on the x-axis, right here. So reals on the x-axis, and then the imaginaries on the y-axis. And they're of the form a plus bi. If you know you're on the complex coordinate plane, you could just list them as a comma b. But the b is the imaginary part, the a is the real part. Okay. And if you want to find the absolute value, which is known as the modulus of a complex number, if you take a course in complex analysis, you'll talk about the modulus quite a bit, of a complex number, you just have to think about, what does absolute value mean? Right? If absolute value means distance from 0, then what would the modulus, do you think, be of a coordinate like a plus bi? If I'm out here, let's put a dot here, this is the point a plus bi. I've gone out a and I've gone up b. This is the modulus that I just drew. So what do you think the equation of the modulus for a plus bi might be? And what's it? Absolute value means distance from 0. So think in terms of distance. So what is my distance here from the origin?
1.
It's like C. On the unit circle it would be 1, yeah. But it's kind of like C, the hypotenuse of the right triangle. What would the equation be for C finding the Pythagorean theorem? Yeah, so that's what modulus is. So the modulus here, and this is how we write it. Okay, so it's the modulus is a plus bi. We symbolize the modulus with absolute value symbols around the number a plus bi is equal to the square root of a squared plus b squared. It's exactly the Pythagorean theorem. So this is how you find the modulus, absolute value, or length, distance away from 0 of that complex number. So, you think you could plot each complex number and find its modulus here? Let's look at a couple of these. I think we'll just do a couple of, well, maybe do 4, but might do a couple with you. Let's take 3 plus 2i. 1, 2, 3 out on the real axis. 2 up on the imaginary. There's the point 3 plus 2i. It is 3 plus 2i. Can you find the modulus of that? A is 3. E is 2. 9 plus 4 is 13, so that's square root of 13. And all that's doing is telling me the distance from the origin out to this point 3 plus 2i is root 13. It's telling me the distance from the origin out to the point 3 plus 2i. Why don't you go ahead and see if you can find the modulus of b. It will come out as a whole number. So go ahead and draw a picture of it, plot the complex number, and then see if you can find its modulus. There's a picture of approximately where it would be in the fourth quadrant there. What do you get for the modulus? Alright, so did you get a value for the modulus? You get 8 is correct. That's it. 4 root 3 squared is going to be 16 times 3, or 48, and then negative 4 squared is 16. 48 plus 16 is 64. Square root of 64 is 8. What about the next two here? Just something to think about here. If I graph this one, square root of 5i. Square root of 5 is somewhere between 2 and 3. Maybe right about here, I'll put a dot. So there's root 5i. What do you think the modulus would be of that? I don't have another, I'm right on the axis. Yeah. Modulus of root 5i is just equal to root 5. Now, if you wanted to, you could use the formula. You could use the formula if you wanted, but what you would have here, if you use the formula, is root 5 squared. What would the other component be? 0 squared, and that's going to end up being root 5. So if you're just on the axis, the modulus is just, remember, it's distance from 0. So how far away from 0 am I? Root 5 away from 0. So right here, the modulus of the real number is only a real part, 1, 2, 3, 4, 5, 6, 7, negative 7. So there it is. The modulus of negative 7 would be equal to 7, yeah. That's it. All right. So that's plotting a complex number and finding its modulus. Okay, the modulus is going to be known as R when it comes to finding polar form here. Okay, so modulus is R. You with me? And then we're going to need to figure out how to find theta. Well, finding theta here just amounts to doing a little bit of trig with tangent. Okay. Yeah.
How did you do B?
Did I do B?
Mm-hmm.
To get 8,
Yeah.
I took 4 root 3 squared plus negative 4 squared, and then took the square root of it. 4 root 3 squared is the same as 16 times 3. So 16 times 3, which is 48, plus 16, and the square root of 64 equals 8. Alright. Polar form. So, looking at this picture over here to the right, if this is theta, this is A, this is B, here's my real axis. R, remember, is the modulus. Okay, it'll be our distance from 0. I could set up the following trigonometric equations. Cosine of theta would equal adjacent A over hypotenuse. So A over R. And sine of theta would equal opposite B over hypotenuse, B over R. And if I rewrite that in terms of solving for A and B, it looks like this. A equals R cosine theta, and B equals R sine theta. Okay, remember the goal here. We're going to take A plus BI, which is complex rectangular form. Okay, complex form, but these are rectangular coordinates. In other words, they're on the, well, sort of like the XY plane. It's on the real versus imaginary plane. And we're going to change that into this polar form for complex numbers. So if I know that A is equal to R cosine theta, I can substitute for A R cosine theta. And if I know B is equal to R sine theta, I can substitute R sine theta for B. And then I also have this I right here. Pretty similar. A lot of students kind of get confused between changing from rectangular to polar coordinates on the real number field versus the complex one, because it's pretty similar. This is the complex field, and I know I'm in the complex field because of this little I that's attached to both of these, okay? As opposed to the other one, we're just a coordinate in parentheses, remember x comma y or r comma theta. They're not written in a vector form with an I attached. So that's how we know the difference between the two. Process is pretty much the same in terms of finding r and theta. So if I factor out an r here, I'm left with r, and then I have cosine theta plus I sine theta, which is exactly what I have up here on our learning target. That was our goal, is to be able to change that form. You got to be able to find r and theta, and we know how to do that already. Okay, it's the same process that we used on the others. Now, sometimes we'll write this as r. It's called cis theta. R cis theta. I don't actually need the parentheses around it here. R cis theta is shorthand for this. It has a C to represent cosine, an S to represent sine, and you'll see the little imaginary I in between them. You're welcome to use that, unless that's confusing for you. But R cis theta is our shorthand for R cosine theta plus I sine theta. So you can use either form. I read both. But R cis theta if you'd like to, because the form is the same every time. It's always cosine theta plus I sine theta. What changes each time? R and theta is what changes. That's it. So if you'd like to write it in that shorthand, you can. All right. It says express in polar form. So we're going to rewrite -4 plus 3i in polar form. Might be helpful to draw a picture of it first. Here's my real, here's my imaginary. I'm 1, 2, 3, 4 to the left, and 1, 2, 3 up. There is the point -4 plus 3i. And so what I want to do is write it in R cosine theta plus I sine theta form. Here's the goal. Write it in this form. Right here. So how am I going to find R? But we're just to find R, though. We just want to find R, and then we're going to plug it in to that form. Yeah, it's a squared plus b squared, and a in this case is -4. This is exactly what you did with the rectangular coordinates when you were changing it to polar. You had to find r and you had to find theta, right? You just have to write this in a little different form. You're attaching cosine theta and sine theta. So r equals is a 3, 4, 5 right triangle, right? So it's 5. And theta, how do I find theta? Say it one more time. Nope. Let me draw it. Here I found this is 5. We know this is 3, and we know this is 4 here. Here's theta. If I want to find theta, and I have a right triangle, the opposite side is 3, the adjacent is 4. You could actually even use sine or cosine to find it, but typically we use tangent. So I have theta equals inverse tangent. Now, here's the thing, guys. It's inverse tangent of, we'll just write down the formula, b over a, which in this case is inverse tangent of, what's b in this case? 3. B is 3. Remember, it's an A plus BI form. We'll just write that down again. And so B is 3. A is negative 4. So it's inverse tangent of 3 over negative 4. Now, which quadrant is my calculator going to give me an answer? Like, what is the output going to be in terms of which quadrant? It's going to be the fourth quadrant, yes. Because the functional output of tangent is always between negative pi over 2 and pi over 2. So it's going to give me a solution down here. So what do I get for my theta here? Go ahead and plug it into your calculator, please. Yeah, that's the degrees. I said to put arguments in radians, so could you go ahead and change your calculator to radians if you could for me? It's pretty common to use, when you're using this cosine theta plus I sine theta, to use back in radians. Negative 0.64. Okay. So negative, let's call that, I don't know, we could maybe call that alpha. That isn't actually our theta. But alpha equals negative 0.6. I got negative 0.644. That's carrying it to the nearest thousand. So I agree. That's what I got. It's giving me, though, this angle over here, guys. This is the angle I just got. This is alpha right here. That's alpha. I'm going to mess it up. Let's do it right here. There's alpha in red. All right, so what is theta actually equal to then? What do I have to do to get theta over there? Add 180, yes. And what is 180 degrees equal to in radians? Pi. So theta is equal to pi plus alpha, which is pi plus negative 0.644. And so theta equals what? It's going to be 2 point something, huh? I got 2.498. 2.498. Should get when you type that in your calculator. So, here's what I've done. I've changed this now, finally, to polar form. And so this is equal to, R was 5, and then I have cosine 2.498 plus pi sine of 2.498. Or if you'd like to, you see the advantage of cis? You only write the angle once. So it's 5 cis 2.498. And if you can get used to writing in that form, that's how we, as you go on and back. If you're actually using this a lot, you're going to use cis over and over again. There's no need to write cosine theta plus sine theta. But I'm going to write both as I go through the notes, so that you know what we're talking about. This is the form, polar form for a complex number. Remember, it's complex if it has the I in it. Use that format. All right, a couple more here to try. All right, B. Let's see. Let's draw a picture of this. So negative 3, and then negative 3. This is negative 3 minus 3i. So real quick calculation for r. R is going to be equal to negative 3 squared plus negative 3 squared. 9 plus 9 is 18. Square root of 18 simplifies to 9 times 2, or 3 root 2. It's 3 root 2. This is one of the ones where it's pretty easy to find the angle. I think we could find it just from the picture alone. Right? If I am 3 left and 3 down, what is that angle right there? Yeah, it's a multiple of, it's right over, right angle. This one, the other pi over 4s aren't in here, it's funny. So it is, but it's a multiple of a pi over 4. We're going all the way around. There's 180, we're adding another 45. That's a 225. Do you know what that is in radians? You can look at your unit circle. 5 pi over 4, and then you're done. So theta equals 5 pi over 4. If it's something that we know in the unit circle, you can probably tell from your picture what theta is, and most of them will be like that. I started with the hardest one. So we have this thing is equal to 3 root 2 cosine 5 pi over 4 plus I sine 5 pi over 4. And we're done. So we've changed that complex rectangular form to complex polar. I'll do just one more here. Root 5 is somewhere in between 2 and 3. Root 11, somewhere between 3 and 4. So somewhere down here would be this point. And thankfully for this one, we're in the 4th quadrant. You could probably leave it as we could actually leave it as a particular negative value if we wanted to. What you'll oftentimes find in my answers, it looks like I'm just looking at my note here, I have the theta is between 0 and 2 pi. So we can do that by just adding 2 pi to our answer. But this one you could leave it negative as a negative. So r is equal to square root of root 5 squared plus root 11 squared. So 5 plus 11 is 16. I get r equals 4. And then theta is equal to inverse tangent of negative root 11 over root 5. That's not one of the angles we know in the unit circle. So you plug it into your calculator. And if you plug in inverse tangent of negative root 11 over root 5, let me know what you get here. It's going to be something in the 4th quadrant. You'll get a negative angle. Put a negative on it in radians. So if you're in radian mode. Yeah, that's what I got. Negative 0.978. So one possible solution would be just write this as 4, and then if you want to use cis form, cis, negative 0.978. Or if you're asked for, or if you're checking your answers, what I've done is I've given you the positive value between 0 and 2 pi. Okay. So you might see 4 cis negative 0.978 plus 2 pi if you want theta between 0 and 2 pi. Okay. So if you want theta between 0 and 2 pi, you just add 2 pi to your negative 0.9728, and you end up with 4 cis 5.306. Remember, 2 pi is 6.28 approximately. 6.28 approximately. So 5.306 is an angle between 0 and 2 pi. So you might find that as you're looking at solutions that I will put the positive angle between 0 and 2 pi in there. Okay, but both are correct. All right, so that's changing the polar form. So now, why would we even want to do that? That's what the backside is going to do. There are some formulas for multiplication and division. And then later on, we'll look at taking them to higher powers. That's what we'll do in 9.3b. But there are some formulas for multiplication and division that allow us to easily multiply two numbers that are in fourth complex form. All right. Okay, so it says Z1. In complex analysis, we oftentimes use Z to represent a complex number. So Z1, that's subscript 1, equals R1 cosine theta sub 1 plus I sine theta sub 1. And if Z2 is R sub 2 cosine theta sub 2 plus I sine theta 2, then the formula for Z1 times Z2 is the following. What that's saying is you multiply the radii, multiply the r's, the radii, radiuses, if you will. And what do you do with the angles? We add the angles. Yeah. It's kind of like when you are multiplying two bases that are the same for exponential functions. What do you do with the powers? Add them, right? There's a connection there with this. I'll have to show that to you later on, but we'll just focus on this for now. So if you want to multiply two complex numbers in polar form, you multiply the two radii and you add two angles, and you'll have your answer. When it comes to division, you divide the two radii and subtract the two angles. That's it. What's behind the proof of this is if you just take two numbers in generic polar form and multiply them out, distribute, it's a mess, and then you use a trig identity. You use the actually cosine addition and sine addition formulas to rewrite it in this form. So that's what's behind the proof. There's an identity. It's the sum and difference. Actually, cosine addition. They're both addition ones, but cosine addition and sine addition formulas. So here's how this works. If I want to multiply these two numbers that are in polar form, it goes like this. You take 2 times 7 and multiply them together to get 14. And then you take the two angles and add them. And that's it. So 2 times 7 is 14. And this is cosine of pi over 12 plus 3 pi over 4. If you think of this as just multiply by 3 over 3. Multiply by 3 over 3. So what I really have here is 9 pi over 12. 9 pi over 12 plus pi over 12 is 10 pi over 12, or 5 pi over 6. Yeah. And I'll get the same thing when I add the same angles over here. Okay, the angles aren't going to change. Plus I sine 5 pi over 12 over 6. Most of the problems I give you you'll be on the unit circle, so you can calculate it in your head without using your calculator. Okay, if it's an angle you don't know, then you'll have to use your calculator. But that's polar form. So this right here is polar. Just label this. So I've done the multiplication in polar form. Sometimes what we'll do is we'll take something in rectangular form, change it to polar, do some arithmetic with it, really. It's complex arithmetic, but arithmetic nonetheless, multiplication, division, taking things to high powers, taking things to roots of things, and then change it back to rectangular. So how do I change this back to rectangular? Well, just a little bit of substitution here, or evaluation. What's cosine of 5 pi over 6 on the unit circle? Root 3 over 2, that's right. Plus I, what's sine of 5 pi over 6? 1/2, good. And so, I get 14 times root 3 over 2 simplifies to 7 root 3 plus 14 times 1/2 is 7. Is it? Am I missing a sign here? Yes. This is negative root 3 over 2, so that's a negative 7 root 3, right? Plus 7i. So looking at my picture up here, that's how she got the negative in here. We're at 5 pi over 6. And so this would be labeled rectangular. Now both of these numbers are in complex form. So you might want to think of it as polar complex. This might be helpful for now. Rectangular complex. As opposed to what we did last time. It was just rectangular and just polar because we were real numbers. This is polar complex, rectangular complex. Once again, how can you tell that this is complex or not on the real number field? The I. It's written as components with an I attached. As opposed to the other ones were written as something comma something, right? X comma Y or R comma theta. All right, what about division? Using our division formula here, root 20 over root 5, we just divide them. And then we have cosine of 5 pi over 18 minus pi over 9. This time I'm subtracting the angles. Plus I sine of the same thing, 5 pi over 18 minus pi over 9. So root 20 over root 5 would be root 4 or 2. So 2. And then we have times cosine of, can you do this in your head? Multiplying by 2 over 2, 2 over 2. So 5 pi minus 2 pi is 3 pi over 18, which is pi over 6, plus I sine pi over 6. That's my polar complex. Polar complex form. And quick substitution here. Cosine of pi over 6 is positive root 3 over 2. Plus I sine of pi over 6 is positive 1/2. And if I distribute, 2's cancel, I'm left with root 3 plus I, and that is my rectangular complex form. Right. That last one on there says convert 1 minus I and 2 root 3 minus 2I to polar form and then multiply. In this case, it would not be difficult to just distribute and then replace I squared with negative 1. Am I doing that? Anytime you have an I squared, replace with negative 1. Not a problem here. But if we want to multiply these two, we could also, as an option, change them to polar first and then use this formula. That's what we're going to do here. Where the real power behind changing to polar form is when you start taking them to powers like this one I introduced to you earlier. 2 plus 3i to the 10th, very simple to do in polar form. Pain to do in rectangular form. Here, you could just as easily distribute and replace I squared with negative 1. Would probably be just fine. But here's what it would look like. So I'll draw a little picture here. See if we can, so it's 1 minus I. So 1 minus I would be right there. Okay, you got a picture of that? Because that way we can get theta, and we're going to get a positive theta, okay? So we'll go positive theta. somewhere between 0 and 2 pi. What would positive theta be to get all the way around over to this guy? You know what theta that is? It's a multiple of, it is a multiple of pi over 4. If we want positive, it's 7 pi over 4. So theta is equal to 7 pi over 4. Good. And what's r going to be equal to here? Can you do that in your head? 1 by 1. So 1 squared plus 1 squared is 2. Square root of 2. Okay. So this one in polar form would be r, which is root 2, cosine 7 pi over 4 plus I sine 7 pi over 4. So there it is. Times, a little picture for this guy here and see if we can figure out the angle and so forth. So 2 root 3 is going to be approximately 2 root 3 or 1.7, 3 point something, I think between 3 and 4. And then minus 2i. So maybe right about here is our coordinate for 2 root 3, comma, minus 2i. So we have 2 root 3 out, minus 2i down. So we got to find our angle here. It is. It's actually one of our special angles. So you're right. You know which one it is? It's farther out than it is down. Did you say it? You're right with 11 pi over 6. Do you guys see that? And if you don't see it, you could use theta equals inverse tangent, but it's going to give you a decimal approximation. So the way I know that theta is 11 pi over 6 is I'm looking at this right here and just reducing this. 2 over 2 root 3 is equal to 1 over root 3 times root 3 over root 3 is root 3 over 3. And then I go, okay, root 3 over 3 I recognize. It's either a pi over 6 or a pi over 3. And based on my picture, the fact that I'm farther out than I am down, I know it's a pi over 6 away from the x-axis. That's kind of what I'm thinking. So theta is pi over 6. R is equal to 2 root 3 squared plus 2 squared. Take the square root of that. 4 times 3 is 12, plus 4 is 16. Square root of 16 is 4, so r equals 4. So I'm multiplying this by 4, cosine 11 pi over 6 plus I sine 11 pi over 6. So now when I go to multiply those two, I just multiply the r's together. So it's 4 root 2, and then it's cosine of 7 pi over 4 plus 11 pi over 6 plus I sine 7 pi over 4 plus 11 pi over 6. I got to add the two angles because I'm multiplying them. So this is 4 root 2 cosine of whatever 7 pi over 4 plus 11 pi over 6 is. Common denominator is 12. So it'd be cosine of, if I multiply that by 3, it'd be 21 pi over 12 plus, multiply that by 2, 22 pi over 12 plus I sine of the same thing, 21 pi over 12 plus 22 pi over 12. And so this is 4 root 2 cosine of, what is that, 43 pi over 12 plus I sine of the same thing. Hopefully I didn't ask you to change it to rectangular form. Why am I saying that? This would be a decimal approximation. It's not something on the unit circle that we do. And I didn't ask you to, for that reason. But we could if we were asked to. All right, so you'll have to come back next time to see the power of changing the polar. So don't go anywhere yet. I got to give you your